Hi everyone. Today I want to talk about vectors. Vectors are extremely important in physics because they can describe many of the quantities we use. Now, we right here have a vector A. This little arrow over A, that just means that it is a vector. But you might be asking, what is a vector? Well, this little arrow I drew sums it up pretty well. A vector is anything with both a direction and a magnitude. Sorry, my handwriting will get worse every time, I promise. So now we have this vector A. And you might be wondering, well, we can kind of see its direction, and we know it's going to have some magnitude, but how might we calculate said magnitude? Well, if you're thinking it's 2 just because it's 2 boxes over and 2 boxes up, I hate to say this, but you are wrong. So what we're going to have to do to calculate this magnitude is, well, we're going to draw one vector that goes 2 to the right, one that goes 2 up, and then we're going to label these. Now typically the x direction is to the right, so I'm going to call this AX. I'm going to call this one AY, because typically the y direction is up in a two-dimensional plane. So now, if we want to calculate the magnitude of vector A, we can use the Pythagorean theorem, which says that a squared plus b squared equals c squared. In this simple formula, A represents one of the legs, which would be either this or this. It can be whatever you want it to be. B also represents one of the legs. And C represents the hypotenuse, which is the long side that connects the legs. Therefore, we can say that AX is a leg, AY is a leg, and A, the vector, is the hypotenuse. And we want to show the magnitude of a vector. Sometimes we could just write it like this, but we could also, to be more precise, write it with these two little bars to the side. Okay? So this quantity squared should be equal to our value of AX squared plus our value of AY squared. To simplify this, we are going to say it's 2 units to the right and 2 units up. So I'm just going to go ahead and write in 2 for each of these quantities. And now we can see that the magnitude of vector A squared equals 2 squared plus 2 squared. Now what we can do is we can add this quantity up. So, you could get out your calculator, but you can probably do this in your head. So it's just 4 plus 4, which is 8, which equals the magnitude of A squared. And now, if we take the square root of either side, we find that the magnitude of A equals the square root of 8, which we can get out our calculators to approximate the value for. Here I have my TI-84 plus, not color. Punch in square root of 8, and we can see it's roughly, we'll call that 2.8. We don't have a unit really, so I'm just going to write units, but always remember your units. So, next, when we want to show the direction of A, that can get a little bit more tricky. So what we can see here is that it's just pointing in this direction, but when we want to put a physical quantity to that, it gets a little bit harder, because we want to write things in math, as that seriously helps us in physics. We don't just want to describe something. It's not an English class. So what we can do is we can introduce the concept of a unit vector. Alright, so we can say that a unit vector has a magnitude equal to 1 unit. This is very important, and you might see why in a minute. So now, if we want to define the direction of our unit vector, well, we're kind of lucky here because we have a choice. We can put our unit vector in whatever direction we want. But we probably want it to describe our vector A. So we're going to put it in the A direction. And we'll represent this unit vector by writing A. And what we'll do is we'll put a little caret over it, spelled C-A-R-E-T. Not the other kind of caret. And when we have this just represents our unit vector. So we also call it a hat too commonly. So we can say that this is the A hat direction. Now going forward from here, what we're going to want to do is we're probably going to want to write an equation because that's what physicists do pretty much all the time. So if we have our vector A here, well, if we think about it, our vector A should be equal to the magnitude of A. Okay, but now we need a direction. And well, our direction's A hat. So we can say that A equals the magnitude of A times A hat. Okay, so now if we rearrange this equation, something we can do is we can divide both sides by the magnitude of A, and we get that our unit vector, A hat, is always equal to the vector A over the magnitude of the vector A. Now if you divide anything by itself in magnitude, you get 1. Okay? Here's why this is so important. We can now represent a value with a direction without changing the magnitude. So it's very important that it's 1, because anything times 1 is obviously itself. So now, if I want to write vector A in a little bit of a different format, something that I can do is I can use the x and the y directions, which is very common for something we call Cartesian coordinates. We'll get more into that later. But, so if we want to write this in the x and the y direction, we first must define our unit vectors in the x and the y direction. So our unit vector in the x direction, I'm going to call x hat. Now, some books and resources like to call it I hat. I prefer x hat because it's very clear what it is to beginners. If we put it in this direction, I'm just going to call this y hat. Now, some books, lectures, whatever, like to call that j hat. I prefer y hat for the same reason as x, so I prefer x hat. Now, if I want to write the vector A in terms of these two unit vectors, well, I can see that A goes over 2 in the x direction. So we can say that the unit vector, not the unit vector, the vector A is going to be equal to 2, which is the magnitude in the x hat direction, plus 2, which is the magnitude in the y direction, times y hat, which just gives it the direction. Now, in the next lesson, I'm going to get into vector addition, and you'll see really why this works. Alright, really quickly here at the end of the video, I want to talk about why vector notation is actually important. It's a pretty modern notation, all things considered, but what we can say is that it's much better than the 19th century notation. So, let me show you this real fast. So, I'm going to show you an example with Newton's second law. It's okay if you don't know it. it's just going to be an example of how simple vector notation is. So if we want to write Newton's second law in the 19th century notation, we have to write that the force in x direction equals mass m times the acceleration in the x direction, and that the force in the y direction equals mass times the acceleration in the y direction. And finally, the force in the z direction equals m times the acceleration in the z direction. Well, this is pretty cumbersome, but we have something better. Let's convert this to modern notation. So what we can use here, we can say, okay, well, this is x direction, y direction, z direction, but we're just going to write it as one vector. So this says that the force vector, much like what we did up there with A, writing it in terms of x and y, we can just write this as one vector, the force vector, equals the mass times the acceleration vector. And the acceleration vector could be in the x, y, and z components. So I think you can see at least why modern notation is significantly better. Just be glad your physics teacher doesn't make you write it out like this. Alright, I think that'll about do it for this video. Thank you for listening. Enjoy your day, night, whatever it is for you.